Hello, so I'm Ian Holmes. I'm going to talk a little bit about something I've been working on over the past year or so, just a little less than a year, on some long context methods for modeling genome regulation. So this is work in progress, and a lot of it is about the methods underlying all this, but these are methods that have come up in a couple of talks already. So I'm very interested to talk with you individually afterwards if you think that these methods might be relevant to the stuff that you're doing. So let me just crack right into it. So I'm going to basically talk a little bit about the goals of the project. I will talk a bit about the data, and then I'll go into reviewing some of these new architectures that are very useful for modeling longer contexts than we can get with transformers. I'll compare the various different methods and see what they've got in common, how they stem from a common root. I'm working in JAX, but we're porting a code base that was in TensorFlow. So one of the first things I had to do was establish parity between those code bases. So I'll talk a bit about how I did that. And then I think that there are some interesting issues that come up when you try and use these methods on genomes. Tal mentioned yesterday in his keynote, these were primarily developed by the machine learning community for natural language processing, some vision processing. There have been a few applications in DNA. This is hyena DNA and caduceus recently, it's bidirectional Mamba. But they're very much on data sets that are sort of standard data sets in the machine learning community. As they get more widely used in genomics, I think that there will be a number of issues that I've run into, certainly, that others may. So I want to talk a bit about those. And then, I'll talk just about some very preliminary results that we have using these to predict genome regulation. So to motivate this, a lot of methods now use this attention mechanism and transformer architecture. We've heard a number of methods of phyloforming yesterday, several talks today. AlphaFold, of course, uses attention, various custom versions of attention, ChatGPT and all the language models use attention. And attention is extremely intuitive and as machine learning methods go, I think, and it's the basic idea is you have to compute a query and a key for every position in the sequences that you're looking at, and then you compare the query and the key, and you use that to flow through a value, to weight a value. And so it's inherently quadratic because you have to compute a query and a key for every position and compare them. And so you end up with this big L by L attention matrix, where L is the length of your sequence. And there are various ways that have been developed to optimize this, because it's proven an extremely versatile mechanism. And one of these ways is illustrated here. This is flash attention. So this pays very careful attention to the memory structure of the GPU. Thinks about the high bandwidth memory and the smaller fast cache in the GPU. So typically the high bandwidth memory is of the order of gigabytes and the fast RAM cache is of order of megabytes. And if you're computing a big matrix like this, you can get significant speed ups by chunking the matrix so that you're only ever basically minimizing the amount of data that you have to move in and out of very, very fast cache in the GPU. And so you can get significant speed up gains by doing this. But you're still working with this fundamental asymptotic complexity of order L squared, right? And you're still somewhat constrained by the memory limits of the GPU. Although again, there are time memory trade-offs you can do with that, and there are various sort of serialized versions of this, or things that run on multiple processes. So there's a few of these sorts of optimizations, but they're all fundamentally L squared. I wanted to add on this slide, I forgot to mention the methods that I'm using, that I'm comparing against. In particular, are these two leading methods developed by the Kelly group at Calico Life Sciences and by DeepMind for predicting human genome regulation. That is to say, they take human genome sequence in, they predict encode tracks on the out, so various functional genomics outputs. And I'll talk a bit more about the training data for those, but I'm basically interested in modeling those. But I think these results should be applicable to anything where you've got long context windows. We've got genome in and information out. Okay, so just to summarize some of the things I was saying, there's these various optimizations to attention that people have tried, but you're always saddled with this L squared complexity. And I would actually say that there's also a cost in agility in sort of model development to having to, the attention mechanism is extremely elegant and simple. Once you start going to these advanced things that sort of do careful GPU memory management and so on, it can become a bit cumbersome. For example, the Informer software and the Borzoi software have a custom positional encoding that uses a binary threshold embedding that they developed after various experiments. It's quite difficult to factor that into the flash attention mechanism that chunks up the attention matrix and passes it in and out of the GPU RAM cache. Although I did end up trying to do it, but it sucked up a lot of time. So this is sort of developer time cost for using these methods. I would say that for genomes, in my opinion, the long context window is even more limiting than it is for natural language, right? I mean, we have a very high dimensionality of token space in natural language. Typically, we operate at tokens that are words or fragments of words. And with genomes, we're typically operating on nucleotides, and the range is extremely large of sort of enhancer interactions and promoter interactions and so on. Okay, so the goals that I really want to try and address are, first of all, just an implementation one. Was it viable to use JAX, which is a somewhat newer technology for implementing machine learning, and it's a very nice high-level abstraction where you just write Python and it gets automatically differentiated, but it's a little bit less mature. So I wanted to answer that question. How does it compare to PyTorch, which is sort of the more de facto standard? The other question I wanted to answer is how do some of these long context architectures compare to transformers? And so that's somewhat more implementation agnostic. To cut to the punchline for both of these, yes, JAX is great. You can prototype really fast in it. It's a little less mature for doing some of that fancy stuff like the GPU memory management that I talked about. There is this new technology, Alice, that promises to give you finer grained control over that. But as with everything else in the JAX ecosystem, a little less mature. Probably will be there within the year, I would say. And then as for these different architectural innovations, big claims have been made about them. There's a lot of excitement about Mamba. I would say that Mamba does deliver on that, and I'll show some results on that. Hyena, less so. For the applications that I've looked at, it does pretty well, but it's not as good as Mamba. The flash attention working in JAX didn't really deliver the same sorts of gains as the custom PyTorch CUDA drivers have done. Multi-resconv, which is a wavelet-based approach, does not really work as well. I'll talk a bit about that. So just to talk about the data that I was training these methods on, there's some 2,000 or so tracks from various different sources, including ENCODE, Phantom, and CZI, separated into this couple different flavors of RNA-seq. There's CAGE-seq and DNA-seq processed with recount, I believe the RNA-seq was, with some sort of normalization type stuff to squash the dynamic range a bit, so it kind of it doesn't overload the output range of the network layers. It's about 14,000 windows, each of which is about half a gigabyte. And the output is pulled into 32 nucleotide bins. So we're not predicting at fine-grained base resolution for these. We're sort of discretizing the output, coarse-graining the output a little bit. Okay, we do various data augmentations on the training here, including reverse complement augmentation and shifting by a few nucleotides left and right during the training loop. This reverse complement augmentation performs really, really well, and a number of people have tried to build in equivariance directly into the network architecture and not found it to be extremely effective. That's a whole interesting side digression I explored a little bit, but I won't go into too much. But essentially, it's pretty hard to beat just reverse complementing your data and reversing all your outputs randomly during training. Okay. So these methods largely that I'm prototyping here largely come from Chris Ray's group and alumni of that group at Stanford. In particular, I'm going to be looking at Hyena and Mamba, but all of these methods grew out of state space models. So I'll begin by talking about state space models. And just to be clear, as shown in the top right of this slide, these are all seek-to-seek models, or seek-to-seek layers that can be components of bigger seek-to-seek models where you've got a sequence input and a sequence output. And so the state space models are essentially, so just to be clear, these are all subquadratic methods essentially, and I'll try and illustrate why they're subquadratic. So the basic idea of these state space models is that they're modeled on these linear state space systems that you see in engineering and in physics, where you've just got some linear ODEs. You've got an input signal, some hidden state that drives, and then an output signal. And these are your sort of seek-to-seek inputs and outputs. And so the clearest analogies are in a system of masses and springs in physics, where the input signal is a force and the output is position, and the hidden state is momentum. And there are some variations of that in mechanics, and then in electrical engineering, you have situations where you've got resistors and capacitors and so on. The hidden state is current, the input sequence is the input is voltage, and so there are various different framings of this, but they can all be expressed using these sorts of linear equations. There's an input, time-dependent input, time-dependent hidden state, and a time-dependent output. I think that the physics system is fine to motivate it initially, but perhaps a more powerful way of thinking about it, and what's closer to what's actually going on, is that there's some orthogonal polynomial basis that you're using to approximate your signal over a finite window using a vector of coefficients. So these are, for example, this is just a random siren-generated sinusoidal-ish function in blue. And then the orange lines are the Legendre polynomial fits using up to 8 Legendre polynomials just over increasingly broad windows. And the idea is that if you want to do some processing of this window, then you can kind of compress all the information about the fit of the signal in that window onto this vector of coefficients. As you sweep across through your input signal, the ODEs, these linear ODEs, describe how those coefficients change. And so there's the Hippo papers from Crossroads group describe this quite elegantly, but this is basically the idea. This perhaps is closer to what's really going on and why these methods are useful. And so the Mamba approach introduces to this the idea of a sort of a discretization that's data dependent. So what do I mean by that? A discretization is essentially how you go from this continuous sort of approach to a discrete signal. Now, typically, if you were looking at a real physical system and really looking at voltage or current or force or whatever, and measuring that over time, then this discretization would be specified for you, right? It's the actual amounts of time between each measurement. When we're looking at DNA, this does not really correspond to time. It's an artificial mapping from the input sequence onto time, similarly with natural language. And you're free to choose actually what this discretization is. And the insight of Gu and Dao developing the Mamba method is that if you kind of work through the math and sort of do a little Euler integration or a finite time integration over each of these time steps, then the length of the time step corresponds very much to the sort of gating step that you see in an LSTM, in a recurrent network. With a longer delta t, so you can think of these A's in the SSM equations as decay matrices, essentially. So if you have thought about rate matrices in phylogenetics, they're very, very similar, right? These are negative semi-definite matrices, negative eigenvalues. And so the signal is decaying with delta t as it goes through the sequence. This is matrix exponential, this e to the a delta t. Longer delta t's, the signal is going to decay more, right? And so the network is going to forget more of what it's seen before and be more receptive to the input during those steps. So if you make this delta t a linear projection of the input, you're introducing nonlinearity in a very sort of controlled and predictable way. And this is probably why Mamba works speculatively. Seems to be why it works. It's essentially doing a gating, LSTM-like gating, but in a more principled way that's sort of based on physical equations. And this actually really helps in developing the methods. For example, in figuring out what the initialization conditions should be for these A, B, C, and D coefficients. You can go back to the Legendre polynomials, you can go back to the physical analogy and come up with sensible values for these, as opposed to just dreaming things up or doing things by trial and error, which has sadly been the case with a lot of deep learning systems. Okay, so I want to just talk a bit about the implementation of Mamba, because this is a detail that's glossed over very quickly in the Mamba paper. I had to spend a while trying to figure it out because I was re-implementing everything in JAX, whereas Mamba is all in PyTorch. Basic idea of the seek-to-seek approach is that there is we can just think of a single channel with the input, actually, because Mamba processes them individually. So we can think of a single one-dimensional input X that then gets expanded into a D-dimensional hidden state H, and then back out to a one-dimensional output Y. And so this is how the coefficients map onto this. And the complexity, if you just went ahead and implemented this as it stands, would be about order LD for this channel, because you've got a sequence of length L and a D-fold expansion from that one channel to the hidden state and back to the output. This doesn't seem so bad. It's clearly a lot less than the L squared of transformers. But the thing is, this happens for every channel of your input. And so it actually is very, very expensive to do this and tends to fill up GPU memory very quickly if you do it this way. Turns out, though, for inference, you don't have to keep that whole hidden state. You only have to keep sweep a couple of columns through. You only ever need 2 columns at any time, the currently calculated column and the previous one. So for inference, you get down to order L. So it's really, really efficient for inference. To compute gradients, though, you still need to materialize that entire H matrix that I showed. So that's rather slow. And so that's where you start needing to implement various tricks. And the particular trick they use is to note that these recursions, these state space model recursions, can be expressed essentially as a matrix product, that the entire recursion can then be written as a product of matrices. And since that is an associative product, an associative operation, you can parallelize it and do it partially in different chunks. You can make it recursive. And essentially the upshot of all of this is that you only need to store L log L space, L log L, sorry, D log L, that's a typo there. So D log L cells in this hidden state. All right, so this is the other method that I'm looking at, and I'm short on time, so I'll just be very quick about this, is Hyena. Hyena essentially starts with the same state space framework, doesn't do the data-dependent discretization. Instead, it does do fast Fourier transform in order to compute the solution to these state space methods. And because of that, it's doing a very long convolution, which naively would be order L squared. With the fast Fourier transform, it's L log L, so it's still subquadratic, but a little worse than Mamba. Hyena does some other stuff to do some gating, which ends up being an attention-like mechanism. I will skim through this in the interest of time. It's a map of everything. We don't need to look at that, but I will share slides if anyone's interested. The last method that I looked at is this multi-resolutional convolution, which is essentially a wavelet-inspired stacked dilated convolution system, a bit like DeepMind's WaveNet. This is not nearly as expressive, doesn't have very many parameters, and unfortunately didn't do very well in my methods. But it's interesting to note that any of these combined convolutions can be represented just as one single convolution, since convolutions are closed under composition. And this is the architecture that I'm comparing to. This is the Borzoi architecture, or rather a very shrunk version of it that fits on an NVIDIA L4 as opposed to the A100s that DeepMind uses for AlphaFold and used for Informer. Okay. I began by comparing my CNNs on JAX to the Baskerville codebase, which is what Borzoi is built on. Get very, very close correspondence in terms of the Pearson-R correlation on the test set. In fact, we do slightly better on the cage models, but other than that, pretty much one-to-one. These are some training curves I will skip through from time. I do want to very quickly talk about some of the issues that are relevant to long genome windows. I will, because I'm so short on time, and I'm sorry I've gone over, I'll just very quickly summarize these and then skim through the slides. So flash attention, you can incorporate fancy positional encoding if you want, takes a lot of effort. Is it really worth it? Probably not. Now most methods use this kind of rotary positional embedding, which is probably an improvement. Bidirectional versions of Hyena and Mamba are pretty straightforward to develop if you look at the math and think about what's going on. I did not use equivariant ones. I just did this data augmentation, as I mentioned, but that can be done straightforward. Probably the biggest issue with using Hyena is that these long convolution functions are generated by a neural function approximator, Siren, this sinusoidal neural network. And the initialization of that is it's exquisitely sensitive to that, because when you have a random function, you multiply it, you convolve it with an entire genome scale sequence, the variance of that ends up being very, very large. Siren wasn't designed for that. You need to scale the output layer to control for that. And finally, I did already talk a bit about the time dimensionality trade-offs in the Mamba implementation. You need this recursive associative scan in order to make Mamba work. So Hino performs slightly worse than the transformer in the tests that I ran. So, Hino is on the x-axis, the transformer is on the y-axis, and you can, transformers on the x-axis, Hino is on the y, and so you can see that transformers performing slightly better. These are PSNRs, so you want them to be high. Skipping through implementation details. This is basically the results that I've got for Mamba versus transformer. And basically this is showing a slight improvement on using Mamba over transformer, but they're really neck and neck. But the thing I really want, the one message I want you to go away with is the training time on these, right? So this transformer, these are both sort of maxing out an NVIDIA L4 GPU. It's about the biggest models that you can fit in one of those. Transformer takes the order of 60 to 80 days to train. These Mambas took 14 days to train. And actually, I told a little fib just then, the Mamba is nowhere near maxing out this GPU. That's just because once I figured out how to do the recursive associative scan, I realized you could cram a lot more Mamba layers in than you can transformers, because the transformer is just so memory hungry. Now, maybe if you use flash attention, you could cram bigger transformers in, but then you're going to run even slower, I think. Okay, so basically, there's lots more room for improvement on the Mamba side. This is just a very early days, but I really just want to say that Mamba does seem to live up to the hype. I think it's well worth exploring. You don't have to do it the hard way like I did going through JAX. There are PyTorch implementations already, so if you're happy using PyTorch, that is fine. I will just skip past the training curve stuff and just thank the people at Calico, the team who supported me doing this. David Kelly, my sabbatical host at Calico, and then in particular Johannes Linder and Divyanshi Shrivastava, very, very helpful in this. So Fanny, Han, and Anya have been a great help as well. It's a really excellent team, and they're doing really great work. And so thank you very, very much.